broadcast news effort there for several years, where he led a group of 4 or 5 people to actually win that competition. It's one of the big government-sponsored speech recognition competitions, or was at the time. And after an extreme amount of effort, they started winning the thing, and basically repeatedly pushed it along. Since then, he has taken over the telephony effort at IBM and is developing research ideas into telephony products. And today, what he's going to talk about is a few things. He's going to talk a little bit about some of his recent ideas on modeling acoustics with Gaussians, and then also combining support vector machines with Gaussians. So, Ramesh, please.
Thanks, Jeff. So today I'll be talking about some of the things I've worked in the last, say, few years, last 2-3 years. And I've sort of organized my talk into 2 parts because there are 2 sort of threads that I really like in the things that I'm doing, and I wanted to say something about both. And they're sort of disparate, but nevertheless I decided to plug them together. So the talk will abruptly stop in the middle and switch gears to something else. Okay, so let's just get started. Okay. So basically, so I'm just going to give the basic setup here. What we do for speech is not exactly this, but nevertheless, it's just good to get an idea of where, things are at a high level. So I'm thinking of a simple situation where you have a classification problem. You have a bunch of labeled examples. X is these vectors in some n-dimensional space, and C are the classes. It could be the speaker, or it could be some class label, and you want to basically find a classifier. You want to train a classifier. So ultimately, your goal is to get some function that maps your data into, a vector into one of the classes. So there are many approaches to doing this. 2 of them, one of the more popular approaches that we all tend to use is use statistical models. There are 2 ways in which you could do it. One is to basically have a generative model where you learn the class conditional distributions and the priors, and then the function is given in this form, fairly standard stuff. Alternatively, you could try to model the posteriors directly, because that's what you're after for classification, because that's what specifies, if you will, the decision boundaries. And then your function is going to be something like this. But then there are other approaches which basically, like, for example, support vector machines, where the goal is basically you specify a class of functions, and then you try to find the best function that minimizes some quantity, like the training error or some regularized loss function. Okay, so that's the setup. And in this talk, I'm going to first focus on standard generative models. That's what we use for speech recognition, Gaussian mixture models. And I'll try to talk about some new ideas for improving the, new ideas for modeling better so that you improve the accuracy. That's one. Next, I'll talk in the second part of the talk about how, some ideas like discriminative techniques like support vector machines can be combined, with Gaussian mixture models to get improved accuracy. Okay. So the basic setup for Gaussian mixture model is the conditional density is given as a Gaussian mixture with priors, means, and covariances. And so each class could have a collection of Gaussians, but to make life simple, I'm just going to say the Gaussian mixture model, basically your data is modeled by a bunch of parameters. So what I'm just doing is what we always do for speech. Pool all the Gaussians of all the classes together, and so there are about j Gaussians total in the system. And this is what I mean by Gaussian mixture model. So the parameters are the priors, the means, and the covariances. Now, everybody knows in speech recognition, we always use diagonal covariance Gaussians to a large extent. And that's because, for large vocabulary systems, if you want to do broadcast news transcription and get a state-of-the-art performance, the number of Gaussians you tend to use is such that you will have to use diagonal covariance Gaussians. For several reasons, computational is one of them. Storage, you can't even store all the parameters in 2 gigabytes, let's say. And data sparsity issues. You only have so much training data, and so usually people tend to use diagonal Gaussians. Now, so when you have a model like this, like a Gaussian mixture model, and you have constraints, for example, diagonal Gaussians, then you have to ask the question, can I do something like a simple thing like a linear transformation of the data up front so that the constraints that you put in are more valid? For example, can I find a linear transformation of the data so that the Gaussians in your system, these sigma j's, are roughly diagonal after the transformation? And that's a good question to ask. And that's a good question to ask for any constrained model. And indeed, this exact question was asked a few years ago for the diagonal covariance case. And the answer is what I call maximum likelihood linear transformation. And it's also essentially the same thing as the global semi-tight covariance of Mark-Gales, if you're familiar with that idea. But basically, I like to think of it more as a linear transformation. You'll know why as the talk progresses, because this viewpoint generalizes in a nice fashion. OK, so the idea here is basically, so you have your data, and you assume that, let's assume you linearly transform the data by some matrix A. A has to be non-singular, but I'll ignore that for the moment. OK. So what I'm saying is y, which is A times x, is modeled with a Gaussian mixture of the type that you had before. So, which essentially means that x, on the other hand, is modeled with parameters of this form, right? It's fairly, it's obvious, right? So now the thing is, so what you have is a mixture model of the data, which is in some constrained fashion like this, okay? And maximum likelihood estimation of the parameters is sort of a generalized EM. What you do is basically first, you fix all the parameters and estimate A. So fix all the other parameters and you estimate A. And this can be done by nonlinear programming, and that's what I suggested in the work I did. But later on, well, at the same time, Mark came up with the same idea, but he had a cuter way to do this. This is a row-by-row update strategy for A. I'm not going into the details of it, but basically I just want to mention that there's a nice algorithm for doing this estimation of the linear transformation. Once A is given, the rest of it is standard stuff, right? Because once A is given, I might as well pre-multiply my data, get Y, and model it with a diagonal covariance system. So it's basically the same training code. In fact, it's the same decoding code too, right? So this is this idea of a maximum likelihood linear transformation. And the advantage of it, obviously, is that it models data better, and so you get better accuracy. And there's no computational overhead, because all you do is pre-multiply your data by a linear transformation. And since we tend to do capsular transformation for speech recognition, this is like you can absorb it in that transformation. Therefore, there's absolutely no computational overhead for doing this. So running systems with capstrectomy at this stage is actually a bad idea. You can always do better.
Just before you go on, if you back up a couple of one slide.
Yeah.
So you haven't lost any generality, right, by saying that x is A times, or rather, there is some y and A times x is y. What I'm thinking is, you had originally a class conditional density assumption for the x's, and then of course the marginal of x will come out to be some bigger Gaussian. And now you're saying that's really some linear transform of some other set of Gaussians y.
Right. So
have I lost any generality here?
With respect to the full covariance, you have lost some generality. The fact that after linear transformation, everything is going to be modeled by a diagonal transformation is a constraint. Okay. All I'm trying to do is, so think of it like this. Full covariance, you have a certain likelihood of the data, the maximum likelihood, you obtain that. If I say I'm going to use diagonal covariance, I'm going to take a hit in likelihood. It's going to be much smaller, right? Because diagonal covariance, obviously, you have less parameters, your likelihood value total will be smaller. So what I'm saying is if you linearly transform the data, you can get somewhere in the middle. And that's exactly what MLLT does.
Is it losing generality because you've got the same age for all classes?
That's my question.
Yeah.
The fact that originally things were dependent on class, and now you're saying...
That's exactly right. I mean, you're tying the A's between all the classes, and that's precisely why it's worse than full covariance, but it's better than diagonal because of the A that I have in there. So it's right in the middle. Exactly, that's exactly right. OK, so that's what the MLLT is. Now I just want to come to this new idea that I want to talk about today, which is called multiple linear transformations. So the basic idea here is very similar. So earlier in MLLT, you had a linear transformation, which was a square matrix n by.
I'm still a little... Let's go back to the previous slide.
OK.
So you're saying that you're not going to model y as A times x, where A is a mixture of, rather like marginal version of the class conditional things with a P of C, and then estimate your A. You're going to basically assume that x is Gaussian with a different...
That's right. I'm going to directly... So the reason why I write it in this form is because in this fashion, I can estimate all the parameters in one shot. And I get the linear transformation and the parameters mu, pi, and d.
Yeah, because I was thinking that I could pose this a little differently. I could say, let's say x is distributed as a mixture of C class conditional mixtures of Gaussian.
Okay.
So X is a mixture of mixtures.
Right.
And now estimate the A, which will make it whatever, close to diagonal or whatever it is that you want.
Right.
But you're not going to do that. You're going to say, I'll forget the fact that X is a mixture of mixtures. I'll sort of
Right.
collapse them and get a gigantic mixture.
Right. If A is shared globally, they both are the same. If A is not shared globally, they are different. So in other words, each class will have an A sub C, let's say. But what I'm going to talk about actually sort of nicely generalizes both. So I'll get to it in a second. So I'm getting there. Okay. So the basic, okay. So essentially, what you do here is something like this. Let's look at the practical scheme of what really happens in this new model. You take your data vector X, you multiply it by some matrix A. This is a rectangular matrix, a tall matrix. Okay. So essentially, you've taken, say, 39-dimensional vector, Kepstra, whatever. You do a linear transformation, out pops a vector of size capital N, which is somewhere between 39 and n times the total number of classes. The reason for that is, it's going to be obvious, basically because if for every class I have, for every Gaussian I have an A matrix. Okay, that's like n rows. And if so, n times j, the maximum I ever need to even get to full covariance performance. Even this is too much, but I won't go into that right now. Maybe I'll talk about it later. So anyway, so this is basically that you take in linear transformation, and then for every class, basically what you do is you pick a subset of size n of the rows. You pick n rows. Say Gaussian 1 has n rows of this tall matrix. Gaussian 2 gets another n rows of this matrix. Okay? So everybody picks, and that picking is specified by a selection set Sj, which means Gaussian j picks a certain set of n indices from 1 through capital N, specifying those rows of A. If you do that for every Gaussian, what I'm saying is basically, you can have its own sort of, within quotes, feature space, which is Aj times X. I'm going to call that Y sub j, for example. And the assumption here is that Yj is modeled with the diagonal covariance, as we did before. Okay? So equivalently, X is modeled in this particular fashion. Okay? So
that's the same thing as saying you've got a big Gaussian with block diagonal, essentially. You're not modeling, if each Gaussian, things are still jointly Gaussian because if X was Gaussian, then
yeah.
of course Y is jointly Gaussian. So you're just saying that you're not modeling the dependencies between the different Gaussians because you're modeling separate Gaussians.
In the extreme case, if it's n times j. But if it's somewhere in the middle, the selection process is tying things in a very strange fashion. Okay, so it's not, right? So in the extreme case, you have each guy is having his own covariance. In this case, you have diagonal, which is MLLT, let's say. And in the middle, it's what I call, that's the place where we're playing this game with MLT. So in terms of the covariances, you're modeling the covariances in this form. So you could directly look at the problem and say, here is my model. Okay, these are the model parameters. But the AJs are specified by giving an A and an SJ together. Okay?
And the AJs
right?
are full type.
The AJs are going to be full matrices, right? For each class, it will be a square matrix because you're picking exactly n rows of capital A in at the top, right? So here's an example. So imagine a simple case where you have, 3 rows. And class 1, this is basically the matrix that you use for class 1, or Gaussian 1, and this is what you use for Gaussian 2. So you just pick so the selection says pick the first 2 rows, and the other one says pick the first and the third row, right? And that's basically what it is. So as long as I know A and S, I can just pre-multiply the data and get these Yj's, and then I'm in the standard diagonal covariance setting, right? So this also shows you why this sort of technique is computational advantageous, because what you do is you take a 39-dimensional vector, take it to a large dimensional space. Each class picks a subset and does the standard calculations. So the code doesn't have to be changed in the back.
So if you copied the first row over, you'd get the block diagonal case. Not the block diagonal case, I suppose. You could emulate the block diagonal by saying, okay, although S1 and S2 share the first row of A, I'll copy it and make it a 4x4 universe
Right.
or something.
Right. Yeah, and you can go all the way to extreme case of full covariance too, right? This covers diagonal to full covariance in a nice fashion. You just control it by controlling the number of rows you have in A. Okay, so now next I want to just talk about how you estimate the parameters here, and then give you some results. So is the model clear? Because this is the most important piece here. All you have is a nice rectangular matrix, and each Gaussian picks its own subset of n rows there, And that will be the linear transformation I apply, after which I'm just going to use a diagonal covariance model. Yeah?
Are there any constraints on the age that you'll pick out? They're required to be...
There are some constraints, as you might guess. After you pick the n rows, these AJs have to be invertible, right? But that's the only constraint you really need. And in the design process, we don't have to specify it because generically, if you pick rows, they'll be non-singular, so it's not a problem. Okay. So like I said earlier, so the parameters are basically the A matrix, the selections for each of the Gaussians, and then the rest of the standard parameters, pi's, mu's, and let's say the d's.
Could you just give a little bit of the motivation?
Okay.
So what's the problem and what?
Okay.
How does this? So obviously.
So what we're
motivation.
right. Okay. So what we're trying to do basically is, we're making the assumption that a full covariance model is sort of the best you can do. Okay, this assumption I'll later on say is not correct, but anyway, that's the basic idea. So you want to approximate full covariance models, but you want to do it with as little computation as possible, as little storage as possible, and therefore, and we know diagonal covariance have all those nice properties. So you try to model everything with a diagonal covariance, but try to get the covariance structure of a full covariance by an approximation process, and the hope is that by having this rectangular matrix where capital N is probably of the order of 3 or 4n, which is far away from 3, is much less than j, which is the number of Gaussians, you may still be able to model them in a full covariance fashion approximately, and that approximation is good enough that you would get the performance of a full covariance system. That's the goal. So try to get full covariance performance with diagonal covariance computation. How do you do that? That's basically, that's the essence of the talk. So that's basically the setup. So you have these parameters. Now, and then it's all standard stuff. You do the E step, you find for every training sample the posterior probability of a certain Gaussian, okay? And here I'm going straight to the Gaussian, sort of keeping classes because it makes life a little easier. And in the M step, you maximize the, this expression with respect to the remaining parameter, with respect to the parameters in the system, which is all these A's, S, pi, d, mu, and d. This is basically just the standard log likelihood of the Gaussian. And if you notice, it's basically I plugged in just the values for mu's and sigmas into the standard expression. So there's nothing complicated. It looks messy, but it's basically the standard expression. Okay, so the first thing I'm going to focus on, how do you estimate pi, mu, and sigma and d, which like I said earlier, is, as you can expect, is going to be fairly straightforward. All you do is basically, based on the posterior that you have, this guy, you essentially compute this, the sample prior, the sample mean, and the sample covariance. Once you do that, the optimal values for the parameters are basically given by exactly this. Mu j is transformed by aj, so it's going to be aj times mu j. And similarly for that, it's just a sigma A transpose and its diagonal estimation, right? So this is easy. But this assumes that essentially A and S is given to you. So how do you estimate those two? That's the next issue. So at least 3 of the parameters are standard, straightforward. We only need to estimate A and S. Okay, so what you do then is, for a fixed A and S, I've already shown you what the expression for the maximum likelihood, the parameters that maximize the likelihood with respect to pi, mu, and d. You substitute it back into the likelihood expression, and you get an expression like this. Yeah.
Sorry, so maybe I'm wrong about this, but I thought that you said that the different AJs might have some common elements of this big A matrix. If you have this big rectangular matrix,
That's
you might
right.
take the first and the third,
Right.
and stick it into A, kappa A.
Right, right.
So this equation here and a previous equation, so essentially you're saying that you're tying certain rows of some of the kappa A sub i's together, and these equations don't show that.
These equations actually show that because I've written the expression in terms of the AJs, which are
There's
functions.
nothing there that shows that, for example, the first row of, say, A sub 1 is the same as the second row of A sub 5.
I've not explicitly represented it, but it's there. This equation sort of hides that. Right. But yeah, you're right. In fact, in the estimation step, actually in this, I'll come to it in a second. But so essentially, you have an expression for the likelihood, which is obtained by substituting the best values for pi, mu, and sigma. And
the reason why I say this is that if you take derivatives with respect to, say, a particular family, that has to somehow be made explicit you're about to take derivative.
Right. Yeah, I'm actually, yeah, well, to do the calculation, you do take the derivatives and set it to 0 and all that. But I really don't want to go into the details of that because it's not relevant. What I want to get across is the idea of what is difficult, what is not, and what we do. So you have some expression that's a function of a and s. Let's fix s for the moment. And you want to maximize this with respect to a. This is just some nonlinear function you want to optimize. You give it a standard optimization package, you get an answer. So a estimation is not difficult either, assuming you know s. Okay? And it also turns out that the idea that Mark Gales had for the square A matrix, the MLLT case, can be sort of modified. In fact, yeah, it has to be modified because you don't have, there you get a simple quadratic to solve, it turns out. Here you can't do that. You get a convex problem, you have to optimize it, blah, blah, blah. Anyway, the details are not important. All I want to say is you can either go through a standard only optimization or you can do a simple row by row update. In either case, you can estimate A given S. Now, maximizing the same function with respect to S is very difficult, and for the obvious reason. Basically, S is a selection process. You have capital N of them, and each Gaussian has to pick its own subset of little n. And that is a discrete optimization, and the usual NP hard problems, the usual stuff crops up, and so we can't solve this explicitly. So what to maximize the likelihood. So what we do is, there are two heuristics that I'm going to suggest shortly that we tried, and that give good reasonable results. But the most important message, again, the motivational thing is right here. Computational cost is hardly anything for this model once you build it. So training time, finding the S could be a pain, but beyond that, it's a very simple model to implement.
When you discuss this, are you going to discuss how you start it? Because when you start a switching function, you sort
Right.
of freeze out.
That's exactly what this is. Yes. So I said there are two approaches we tried. The first approach, so initialization. The first approach basically is a bottom-up clustering approach. Here the idea is, okay, I'll start with a full covariance system and then try to tie together some directions to get to the thing we want. So let me explain what it is. So we start with an A matrix that's obtained by, you take all the sample covariances, you find their eigenvectors, and you stack and write them as row vectors, and you stack them. These are the eigenvectors of Gaussian 1 up to Gaussian j, all row vectors. Once I have this A, the selection, I could just say the first Gaussian picks the first n rows, second Gaussian picks the second n, and so on. I have a full covariance model right there. So that's the best likelihood I can get. Okay. Now the goal is then to merge rows in some fashion such that you don't lose likelihood too much. And if you do some process iteratively, hopefully we get to a size capital N, which is what we want. Okay. So the way we do that is basically you find pairs of rows which are not pointed to by the same Gaussian. And that's for the obvious reason, because you have n rows. If you collect the two, then if you merge the two, then what happens is that Gaussian is rank deficient. Okay, so that's very simple. So with that one constraint alone, you try to define all possible merge pairs. This is a lot of them. It's painfully expensive. And you find the best merge in terms of least loss and likelihood. Right. And once you find that pair, basically, you merge the two rows, you drop, since the rows are merged, you drop one of them, and all the S's which you're pointing to that row will point to the row R. Okay, so this is simple stuff. Once you've done that, you have an A matrix which has dimension 1 less. Right? So if we start with an n by k by n matrix, you have a k minus 1 by n matrix, basically. Now, I told you how we can optimize with respect to A. You do the optimization with respect to A. And then you go back to, step 3. Find the best merge, and you keep iterating this process. So you keep reducing one by one the size from capital N, J, from here all the way to the size that you want. Okay, so this is one strategy. We tried this. It works, but it's quite expensive. The second method, okay, so personally, I'm not too fond of this technique, partly because of the following reason. Remember what I said. To get the efficiency of diagonal covariance Gaussian, you must use of the order of about, say, 2 or 3 times little n. That is, 39 dimension goes to maybe 150 or 200 dimensions. But you're starting with number of Gaussians times 39. That's a fairly large space, and you keep clustering. You have to do several iterations to get to the size you want.
What ensures that you maintain full rank of your sub A's, A sub when you merge a row, how are you guaranteeing that each one's matched?
So this choice makes sure that you don't do the stupid thing, okay?
Yeah.
Beyond that, we don't do anything and it just works.
Okay, so you might get a singular.
Oh, it can happen in principle, but in practice, these are, it just doesn't happen, right?
Just doesn't happen, or you don't even bother to check?
Actually, well, code checks obviously, but it doesn't happen, and generically you can argue it cannot happen. So you must be in bad luck for that time. Okay, so the other approach says, okay, now look, I only want about 150 directions. Why should I go to like 30 number of Gaussians times 39? Let's start with the MLLT and do a top-down splitting approach as opposed to clustering all the eigenvectors. Let's start with just the MLLT, which is basically an n by n matrix, and try to add extra rows as and when we need. And this one, we thought of several techniques, and finally we settled on something which is a randomized algorithm. It works, though. And I'll show you the graph showing likelihood increase. So what we do here is we pick a random row, say the rth row of A. And then we say, basically, okay, we're going to split this thing. The way we would split this, we'll copy that row again at the bottom. So you have a k, so if you start with a k by n, you have a k plus 1 by n matrix. And then all the guys that are, all the Gaussians that were pointing to the rth row, now they would either point to the rth row or the k plus 1th row. So in other words, you randomly throw the pointers from the Gaussian to either the rth row or the new row that you just copied, which is when you start with the rth row anyway. And then you maximize with respect to A. The likelihood will obviously go up because you're sort of untied. So you have more freedom. Okay? After you do that step, then we go back and say, okay, look. Now, for every j, such that for every Gaussian that pointed to the rth row, I'll give it now some freedom. I can switch to anybody I want. Okay, so I'm not optimizing A, but I can say, if I do a scan of all the possible A's, is there any other A I could replace my current row with to give me an increase in likelihood? If that happens, I take that switch. And then I maximize again with respect to A, and I do this several times. And this is sort of an ugly algorithm. We didn't know any better way to do this. This is a hard problem. Yeah.
All right, so step 6, is there a way of doing that without having to go through all the data again?
See, the way in which this, remember, if you go back to this here, let me go back. See, the expression here, this thing is, it depends only on the sufficient statistics.
Right.
So you don't have to go to the data ever. Oops. There we go. Okay, yeah. So here I was, okay. And then, of course, if you're not happy with the number you have so far, you go back and try this process again. Yeah.
Instead of picking randomly, is there a way to, for instance, look at the sort of let's say you start in the beginning with the 39 by 39 matrix.
Yeah.
Look at the biggest off-diagonal element in the inverse covariance matrix and say, okay, these two are the ones which are most.
Actually, we didn't try something like that. Let me tell you the first thing we tried, which is in some sense, it is greedily optimal. What we did is we took, and it's extremely expensive, so we had to throw it out. We couldn't do it. What we did there was we took each Gaussian, okay, and we said here are the n directions that this Gaussian sees. This is a globally shared one. If I throw one out and allow you that Gaussian the freedom to put whatever it wants there, what is the best gain in likelihood? I can do that for every Gaussian. And then I find the best gain I get that way and add in that one row. Okay, so that gain was clearly going to be better than what we do here. But it's just too expensive because for every Gaussian, I have to substitute every possible row and then do this. It's too expensive, so we decided to go for this randomized thing, which seems to work. Yeah, it works reasonably. So let me give you any more questions. I'm going to the results section now for this part of the talk. Okay. So what are the results? Okay, so the experiments we ran, okay, so all of this was done in the context of embedded speech recognition in a car, in a moving car. And the kind of tasks that we're interested in are simple grammars like command and control, turn radio to 93.6 FM, that kind of thing. And also digit strings, because you may want to use your cell phone or some phone in the car. So here, these are the numbers on the command and control task. And there were two microphone positions we tried. One is on the seat belt, the other was on the sun visor. And all of the results I give are string error rates because that's what is relevant to this task. I could have given the word error rates too, but qualitatively, basically, the results are the same. So you have essentially the maximum likelihood linear transformation, which in itself is an improvement over the diagonal baseline. So I just thought this would be the better baseline. Here, so it's a 39-dimensional feature space. This is the standard Kepstra with MLT applied on top. This one basically I have n is 156, so you have increased the number of rows up to 156. And you do see a gain in both cases. And in this small task, basically the full covariance number is clearly better than even MLT. Okay? And this is something that I realized only after working on small tasks. In really large tasks, reasonably big tasks, I've tried full covariance without much success. But in smaller tasks, full covariance gives you a big win. And so I'm not surprised when in Aurora, for example, you get gains by full covariance. Now there is obvious comparison to be done. Right. So we did do that, very clean comparison, and it's actually toward the end of the talk, I'll try to, if I don't mention it, just remind me. I'll tell you, what the comparisons are. But in this experiment, at least, we didn't do a clean comparison. This has more parameters than this, and this is more parameters than that. Okay.
Which search method is that?
This used the second search method. Start with MLLT and go from there.
Can you tell me?
Yeah.
So MLT used diagonal covariance?
MLLT used diagonal covariance after the application of MLT,
yes,
correct?
And the MLT used full covariance?
MLT used diagonal covariance after application of MLT. So in both cases, you have some sort of a feature space transformation, after which you just do standard processing. In fact, we use the same code actually for both. So all three experiments use the same code as far as the computations beyond the front end.
So the way the computation would work is a 39-dimensional feature goes in, a 156-dimensional feature comes out, and when you want to evaluate its probability under any given Gaussian,
You pick a
select
subset.
the
That's
subset of 39
exactly, that's right.
coordinates and compute.
That's right. All of this we wanted to do in the context of embedded speech recognition, so we had serious constraints on the resources. So we just said we should do a linear transformation. That's part of the way in which we got to this model in the first place. Yeah.
And what about the decoding process? So what about the test data? Did you apply MLT or MLT or the test data? And if you apply, how can you define the class that
Okay, so whatever you do at decoding time, you basically will hypothesize something and say, give me the score of this Gaussian. When that happens, you've already computed the big vector. You select that subset which corresponds to that Gaussian and evaluate.
and you try to find what the maximum is?
There's no maximization here, right? Because you have a completely specified model. So I wanted to find the likelihood of some Gaussian. I've taken my x vector multiplied by a. I have this big 156-dimensional vector. This Gaussian points to a subset like Sanjeev was saying. You go pick those numbers and pretend it's a diagonal covariance system and just do a standard backend processing. Right? It's exactly the same. And the next task we tried was 711 digit strings. This is for telephone sort of applications from a car. And a slightly bigger acoustic model. And this, I forgot to mention, both cases the number of HMM states or leaves or classes or whatever are about 809 of them. Okay? And the story is basically exactly the same, independently of speed. So this is a stationary car, 30 miles and 60 miles. The same sort of improvements happen in all three cases. Yeah.
The noise at various speeds is it generated or it's?
No, this is real recordings in a car, in a moving car. I mean, this is real product scenario.
Same model for all?
It's the same acoustic model for all conditions. And one minor thing I wanted to mention is, at training time, however, we found it expensive to collect large amounts of data of this type. So what we did is we collected a reasonable amount of data at 60 miles, somewhat more amount at 30 miles, and a lot more at 0 miles. And we would add digitally car noise at various speeds to get the training corpus. So it's sort of a multi-style training or multi-condition training, as you guys call it. So that's fine. But at test time, basically, all these test sets are actual recordings in a car. And it turns out that the SNR at different speeds don't always correlate with speed, because you might have a really good car. In fact, turns out some of the cars we use 30 miles were fairly high quality and better than the ones at 0 miles. In fact, you notice that difference. So this sort of plot, after seeing it a few times, I realized it's better to plot this versus SNR so that it's more smoother variation. But anyway, it's not important. Okay. So now what about the likelihood? So for the two models that we built, this is the digits model, and this is the one for command and control. As a function of the number of rows of A matrix, we look at the increase in likelihood per frame. So the delta likelihood per frame on the training corpus. And the graph looks something like this. The interesting to notice the right corner there. Now we just stopped at some point, but the trend is still going up. Okay? So clearly from 156 if we go to 200 directions, clearly the likelihood will improve. The likelihood has not saturated yet. Okay, so that was sort of the situation probably about 8-9 months ago.
What's the likelihood under the full covariance model?
The likelihood of the full covariance model, yeah, I don't have, it's clearly not in the chart. I don't remember.
Give you an idea.
Yeah, basically, I think it's somewhere up here. I don't remember exactly the number. I'm sorry. So I can't, I don't remember. Okay, but this trend basically convinced me that we should do better than this somehow. The problem that was really bothering us was this discrete optimization. Okay, so since that, in some recent work with Peter Olson, we have come up with a strategy to sort of overcome that to some extent. And we give something and get something in return. So the training thing becomes easier. I'm going to describe it shortly. But at test time, it's a little more expensive than this model. And that's what I want to say last. Okay. So how do you view these things? And this is the reason why I like to call it a maximum likelihood linear transformation also. Basically, if you look at the inverse covariance now, okay, if you looked at the covariance earlier, the dependence on A was something like A inverse, blah, 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 right? But on the inverse, it's basically a quadratic in A. Okay, so it looks like the dependence on the parameters is more explicit for the inverse covariance. Okay, so this is what the MLLT does. Every covariance is of the form some global transformation times a diagonal part times the matrix transpose. What about MLT? So if you write down MLT, each guy has his own AJ, which is obtained by selection, TJ inverse, and AJ transpose. Now the same thing, I can stuff rows into this AJ to make it the full A if you want, by just making sure that I expand this D matrix also to put zeros in there, right? So this exact expression, I can write it in this form, which looks similar to that thing. And there's a reason for doing that. So basically, the difference between MLLT and MLT is that in this case, you have a rectangular matrix instead of a square matrix, number one. Number two, these lambdas are diagonal, and most of the entries are 0, except for the entries that correspond to the selected rows. And that will be just TJ inverse. Okay? So this suggests the following generalization. If you look at this model, okay, I have lots of diagonal entries which are 0. What if I make them non-zero? Okay? The fact that they were 0, most of them, that is capital N minus little n of them were 0, was the reason why we got a lot of computational efficiency, because we just selected the subset. What if I say don't select, but just take a linear combination? In other words, you just allow these lambdas to be non-zero, number one. The second change is the lambdas were positive, and this was because they are inverse variances, and obviously that happens to be positive. But what if you allow them to be negative too? And sure, you can do that, but you have to put in some other constraint. And that's what EMLT exactly does. You write the inverse covariance in the form A lambda A transpose. A is a rectangular matrix exactly like in MLT. The lambdas are diagonal in this 156 dimensional space, if you will, squared space. And you impose the constraint that the whole thing is positive definite. The lambdas themselves could be negative or positive. I just want the sigma j inverse to be positive definite. That's all you need for a Gaussian. The parameters in this model are the rectangular matrix, the pi's, mu's, and this new thing called the lambdas. The lambdas do not have an interpretation of inverse covariance because they can be negative. Okay? So training is easier than MLT. Computation at test time, it's more expensive because you have to compute these quantities. And the numbers you get with this, we were surprised, actually. Quite a bit surprised. 20% relative improvement over the MLT, first of all. More importantly, it's better than full covariance modeling. The likelihood is worse than full covariance, but consistently on test sets, it has better performance. In other words, it's generalizing better. The full covariance at some of the models sizes we tried was already beginning to show some signs of overtraining.
So when you do this in the MLT way of doing things, they have two Gaussian selected the seam row in A, they had the same lambda j.
No, they had different lambda j. Because that was the variance of that particular Gaussian in that direction.
Oh,
The dj is purely a function of the Gaussian.
so the old lambda was just a selection.
Selection with a substitution of inverse variance.
The inverse variance
Correct.
of the Gaussian.
Correct, right. Right.
So this is
Right. So the way to think of MLT is for each Gaussian, you pick a bunch of directions, those rows, and in those directions, I fix the variance or the inverse variance, which is the lambda. In the EMLT case, there is a corresponding interpretation. You're saying pick a bunch of directions, A of them, and fix the covariance in that direction, the variance in that direction for every Gaussian, all Gaussians. Okay, that's another viewpoint which I didn't put down here, but that's another viewpoint. Okay, so that's basically the latest I have in this. Already I've taken 40 minutes. Okay, so I've just, yeah.
On that last stuff,
Yeah.
could you go back to the so for MLP, essentially the lambda j's are the things that you learn with the discrete optimization problem. You learn where the non-zeros are.
Correct.
Which gives you the s's.
Correct.
So essentially, the reason why this is probabilistically valid is because you can think of this as this high-dimensional Gaussian.
Right.
And you're modeling essentially subspace, the hyperplane.
Correct.
Gaussian.
Correct.
It's not, you don't have the problem of different feature spaces because of this.
Correct.
Because of this thing, as long as you allow for singular.
That's right.
Big giant.
Right.
And
So-
in this case, you're saying that the lambdas can be negative.
Right.
And there's no interpretation of the A's as being orthonormal or any being any kind of orthonormal. You have no
No.
idea what the A's are.
A's are not orthonormal. Yeah, they're not orthonormal. Right.
So that's because the lambdas can be negative, zero.
Right.
So two questions. One is, did you do the selection procedure in exactly the same way with either the random thing or the random growing thing or the clustering thing for zeros and lambdas and in a less constrained lambda?
In the less constrained case, basically what we did is, okay, so I'll tell
The
you.
reason why is because I'm wondering where these results.
Okay, the results come like this. Okay, so I'll tell you how we got this improvement. We decided we're going to do 4 times 39. So we took all the Gaussians and split the Gaussians into 4 groups based on the phonemes, fricatives one, something like that. I don't remember the split, but it was based on looking at some book on phonetics. Okay, these are similar ones or whatever. We took that group of Gaussians and said, let's do an MLT for that. Second group, MLT for that. Third group, fourth group. So we have 4 MLT matrices. We stacked them all together. So that was our initialization. And then the lambdas, we just said, go find it. And the lambdas, it turns out there's a unique answer. Well, there's not a unique answer. It's a convex function of lambda. You can show that. So, it's a well-behaved thing. So you'll have all these negative terms, but it's always a good, well-behaved thing. You have a unique answer, pretty much. Generically unique answer.
Okay, but the only question is the effective S's that you got was done by the same method.
Okay.
You're just using a less.
Yeah.
Right, or maybe you can talk about it, right?
Yeah. Basically, this is it has a lot more parameters because remember, each Gaussian has lambda j, which is like, an n-dimensional vector. Previously, I only had dj, which was a little n-dimensional vector. So the number of parameters has gone up tremendously. Oh, yes, this is where I want to answer that question. So in this context, actually, since it's a much, we decided, we had to find exactly why this is happening with respect to full covariance. So what we did is we took an EMLT model with a certain performance, counted the number of parameters, built a diagonal covariance system with exactly, or actually we gave it more parameters. In that ballpark, but more. It was worse. Then we built a full covariance system saying you take all your parameters, whatever you want. Okay? So full covariance has more parameters, yet it's 15% worse. And our only reason for this is, and roughly the size n we used to get that sort of performance was about 8n. So 8 times 39. That's when we got this performance. And the reasoning is basically that just because you're sharing this in some fashion, that is effectively you're forced to make these Gaussians comparable. So there is a level of discrimination that's happening naturally. Okay, but this is all hand waving. I don't have it precise.
So your comparison with the full covariance had an order of n, the size was n, and the EMLT was 8 times n.
That's true, but the thing is that there is a difference, however, right? To get, if you want to get the full covariance, one way to do it is basically to stack 1 per Gaussian. So that will be n will be little n times j. That's the full covariance situation. That's what gives you the best likelihood. And this is actually a special case of it. So it has fewer parameters. Yeah.
So you say you're not comparing the a full covariance system of size 8 and you compare it with n.
That's right, because if you think about it, we are actually modeling everything in the little n dimensional space. We are just playing tricks with how we use parameters for the covariances. Really, the modeling for all these, for both cases, happens in the little 39 dimensional space. Your data is 39 dimensional space. I cannot model in a high dimensional space because I will be lying in a subspace, and therefore my likelihood will shoot through the roof.
But I guess the question that I think Carlos is asking
Yeah.
is that the EMLP system is like a 8n row matrix.
That's right.
So if I'm just counting parameters, what
Yeah.
should I count for the full covariance system?
For the full
And the answer
covariance-
I think is 800n.
No, I wouldn't count 800, half of 800n, because I can directly count the number of parameters in the covariance. It's n into n plus 1 over 2 times j. Right? I can do that. So that's the comparison.
Comparison is 400n.
Yeah, that's right.
How are you enforcing positive evidence at the end?
Okay, so we did two things, and both give good results. In one case, we just said forget about negative lambdas, make them positive. It's supposed to be R plus. Then you have no problems, right? That's positive, definite, obviously. When it was negative, basically, we had to take some real care in terms of the optimization package. See, because the maximum likelihood solution is in the positive definite region, okay? If you do a numerical optimization, make sure that the step size is not large enough. Okay, when you probe, do these line searches, which you typically do. If you make sure that that line search doesn't probe regions where it's negative definite, in which case your likelihood is infinite, right? Then you're okay. So we did that sort of handicapping a routine to make sure it works. But we didn't explicitly, in other words, we did a trick on an optimization routine to make this work. But strictly speaking, and we know how to actually impose this. What you do is you take the gradient, Hessian inverse gradient, take the Newton direction. Make sure that you do a search within the range where you don't go outside of positive definite. You're at a point which is positive definite. You're moving in this space, along a certain direction, the parameter space, which is the A space, let's say. You can make sure that you don't go too far to go out into the. Ultimately, you have to go through determinant 0 to get to negative, right? So you make sure you don't do that, and then you're fine. So it's easy to impose this constraint. It's not very difficult.
Does it make the search take a lot longer?
Search for, what do you mean by search?
If you impose this restriction,
Oh, search is, of course, a little longer. But the thing is, numerical optimization takes 5 hours. It takes 10 hours. Okay, we don't care. Right? I mean, it's not like the discrete optimization where it took days, and we just, right.
Then presumably you could get a situation where there's a boundary maximum, where your search would then fall along the edge of the boundary.
Right.
Where you trying to move outside the space.
Yeah, Actually, the story there is not, we don't. The story there, at least I don't completely understand. That's precisely why I'm not talking about it. You're trying to figure out. There are some things in there which are kind of funny. All we know is that we can play with it and get really good numbers, and we're able to solve problems with it. But nevertheless, the full theory there, we have unraveled most of it, and that's in the NIPS paper. And there's a transactions paper which, pretty much is ready. It will probably go out next week where we have some more stuff. So that's why, that's part of the reason why I didn't talk about it, because some of the things I would like to figure out, best before talking about it. But nevertheless, MLT, this whole idea of modeling the covariance, inverse covariance, is a great idea. That's for sure. At least I'm convinced by. And we tried it on not only, see, this one we couldn't try it on a large telephony database with 500 hours of training data simply because we couldn't do it. EMLT, on the other hand, we did try it, and guess what? It gave us a 15% improvement over an MLT system. So it's holding out on different databases. I'm sorry?
15% absolute?
No, relative, obviously. All right, so wishful thinking, my God, okay. Anyway, so anyway, the summary is basically this. You can actually improve on. There's no need to ever use straight capsule, system. You always want to use an MLT, whatever happens. On top of it, you can do multiple linear transformations and get an improvement. And you probably want to use something like an MLT if you are really concerned about speed at decode time. But if you can give that up and say I'm running an eval type system, then EMLT is a good bet. And also we have some tricks to, after designing the EMLT, find the lambdas that are roughly close to 0 and 0 it. So you can get closer to MLT also. That's also in the transactions paper. If those who want it, you can send me an email or something, I'll send it to you.
Change error at all.
That hurts a little bit. It hurts, but now not as much. You're better off doing that than. So in other words, I could do a 2 cross EMLLT and an 8 cross EMLLT, 2n and 8n. I'm better off doing an 8n and pruning back to 2n rather than right. So that sort of stuff. Okay, so that's all I have for the first part. And the second part, I think I'll have to breeze through. How much time do I have?
35 minutes.
35 minutes, okay. Right, so the second.
Any more questions on
Yeah.
the first part?
Just a short one.
Yeah.
Coming back to the case where you actually can reduce the dimension of your Gaussians, I think it seems to me like you could prove that the probability of that happening is close to 0, if not 0, because the spaces in which you actually make your things become linearly dependent.
You mean the last part where I said you build an 8 cross and reduce it? Is that what you're talking about?
No, when you're, the question came up, what happens when you, I'm sorry,
Okay, we can talk later, right. Yeah. So let me move to this. There's one comment I wanted to make, but let's not do it now. Okay, so in this part, I'm just going to talk about some experiments we did with support vector machines. Basically, like most people, I also believe that the right way to do classification is to focus on the decision boundary. But being in speech, I've never been able to do it in a successful and graceful manner. So we've been plotting on this sort of idea for the past 5-6 years. In the last couple of years, we decided to play with SVMs in a certain fashion, and we have got some results, so I thought it would be great to share this. That's the basic idea. So here, essentially more than in the other case, we are nowhere close to having a story that's complete. In the EMLT case, we are very close. I can see that there is a theory there that makes a lot of sense. Here, it's a little more raw, but so there won't be too many equations. It'll be more like what we normally do in speech, which is a lot of engineering. Okay, so briefly, what are support vector machines? I hope most of you are familiar with it, but if not, I'll just say a couple of things, and that's all that's relevant, at least for the talk. So support vector machines are typically a binary classification problem. You have 2 classes, positive examples and negative examples. And the way you do support vector machines is you take all the positive examples. Here is a schematic in 2-dimensional space. All the positive examples are blue, negative are red. And you try to find a hyperplane, a linear separator that separates the two. And so the parameters are the parameters that describe this hyperplane. And the goal is to make sure that the margin, the gap between the positive and negative examples, this distance, is maximized. Find that hyperplane that maximizes the margin or the separation between the samples. So that's support vector machine. Now clearly in many examples, the samples may not be separable. Then what do? There is a generalization of this called soft margin approach, where basically if you are on the wrong side, you have a loss that depends on how far you're on the wrong side. You add it to the margin maximization term to get another expression that you optimize. But basically it can be handled. There's yet another method to handle the same thing, which is this thing called the kernel trick in the support vector machine literature. Basically what you do is, roughly speaking, you take your data vector, which is in, say, X is in some n-dimensional space. You map it to some large, say, capital n-dimensional space, to use the same sort of term. But this is some nonlinear transformation maybe. You go to this high dimensional space and you work there and find a linear separator between the classes, and maybe you're lucky there. And if you're not, you always have soft margin to back off onto. Okay, that's the basic idea of support vector machines. So some of the advantages and disadvantages. The first thing is it's really good in terms of generalization. It clearly focuses on the decision boundary, and you can actually prove theoretical bounds on how you generalize, meaning how you perform on test data based on how big the margin is on the training data. All this is great, but the bounds that you get by this technique are so far from reality. In other words, you normally perform with SVMs much better than what theory would say, but that's a side issue. Nevertheless, it's good to know that you can actually show that these things generalize nicely. And it turns out the maximum margin separator, as you can visualize in this 2-dimensional example, it's got to be unique. But right? At least it's a convex problem. You have, so the hyperplane is sort of within quotes unique, even though the description of it, maybe the coefficients that describe it may not be unique. So it's got a global convergence, unlike the EM and stuff we use for Gaussian mixture models. Thirdly, a lot of people have been working on it recently. It's a hot, hyped up area, and so clearly, there's a lot of effort there, but it's also shown improvement. So it's definitely, a technique to reckon with. It's an important technique. Some of the drawbacks for using it for speech, or for any problem for that matter, is you have to choose this. I said you start with the feature, original feature space, and you map it to some high dimensional space. How do you map it? What is that high dimensional feature space? That's done through an implicit choice of a kernel, but how do you choose the kernel? So that's an issue. How do you do that? It's not clear. At least I don't think the full story on that has been said yet. But there's one technique you could choose to explicitly map something to a high dimensional feature, and that's what I'm going to be using here in this talk, which is called the Fisher kernel. I'll come back to it a little later. The second problem is basically, I said it's inherently a binary classification technique. So how do you handle multiple classes in this context? And there are some techniques that people have come up with in the past, in 95 or so, by a couple of folks. And so that's the sort of technique that I'm going to try and use in this context. So there are many ingredients to make this happen. I'll go through them. We just followed a sort of a recipe, and I don't think any of them are the best choice, but at least that's where we are. The last problem with SVMs is it just cannot handle large data sets. I mean, handling 600 hours of speech like we did on telephony with Gaussian mixture models is a near impossibility with current day SVM technology. So how do you handle that? There are a lot of techniques that we're trying to develop to handle it. Go on.
Is that gradient of log of theta?
There's a log there. I'm sorry. Yeah, it'll fix itself in the next foil. Just hold on. Just wait. Yeah, it's fixed. So actually, I made these files sometime yesterday afternoon. In fact, a lot of it happened while I was on the train. But so what's the idea here, basically? So I said you want to map to some high dimensional feature space where you're hoping it's going to separate. So the way we do that, at least, one methodology suggested by Yakula and Hausler is the following. Again, by no means is this the best method. It's just a method. And I don't even believe it's anywhere close to the best. So what you do is, let's assume that you have some data. Let's assume you build a model for it. Let's say you build you have some vectors from a speaker. You build a GMM for it. So one sentence, you build a GMM. So you have a bunch of parameters now, right? Now I can go back to every sample, the first sample, and say, hey, look, I take the likelihood of the data, take the gradient with respect to my means and covariances, whatever. I get a fixed size vector now, but it's in a higher dimensional space because the means themselves are in the first dimensional space. Now you have the variances, so it's in a larger dimensional space. Okay? And that's what this is. You take the log likelihood and take the gradient. Now if you have, let's say you have a two-class problem. So I build a GMM from the first class training data, I build from the second class training data. I can take the gradient with respect to the with respect to the first class, I can have the likelihood gradient, or with respect to the second class. So there is an asymmetry here, right? But nevertheless, basically, this particular feature vector is also the standard, what is called the Fisher score in statistics, the standard gradient of the log likelihood. Okay? And what we are going to use in this setting at least is basically something like this. So you have the log likelihood with respect to the parameters of a certain class, and you take the gradient, and that gives you one feature space that depends on the class. So that depends on, for example, the speaker. And if you have every different speaker, each speaker, for example, in speaker ID will have his own Fisher feature space. Okay? So this is the part about mapping to high dimensional space. The second piece is somehow we're going to take a bunch of binary classifiers, SVMs, and get a multi-class decision. I have a speaker ID problem with 52 speakers. I want to find which speaker it is, but I'm going to use SVMs to do this. So somehow I need to get a 52 classifier from binary classifiers. And so then I have to take the scores from these binary classifiers and combine. To make these scores comparable, we calibrate them by doing the following trick. We basically take so what the SVM tells you is, suppose I give you a sample, it tells you how far you are from the decision boundary, the hyperplane in that picture. And that's just some scalar number. So you want to convert that into some posterior so that it's nicely scaled between 0 and 1, and you can take all the outputs from the binary classifier and do something to them. Okay, so that's the idea behind this. The simple, you just learn a sigmoid that maps the score f, which is the distance from the margin, if you will, to a posterior on, say, the positive class, for example. And for the negative class, it's 1 minus that. So here I've just shown how this looks typically. We trained some support vector machine for a binary classifier, and this is what it is. The scores look like this. This is the blue comes from the positive examples. Red from the negative. You train a sigmoid, and you get a nice posterior. Okay. So that's one ingredient we threw in there. The next thing is basically how to go from binary to multi-class in more detail. So the way we do that is basically to make things quick, and I'll just focus on what we exactly do. What we do is basically you take, so we have 52 speakers, let's say you take a speaker and build a binary classifier with respect to every other speaker. So you have C into C minus 1 binary classifiers. Each is a support vector machine. Somehow the scores from all these binary classifiers we have to combine together, and that's what we do. And what we really do is, for each speaker, the score is the posterior score it gets by competing with each of the remaining 52. You add them all together without any weights, just straight addition of the scores, okay, on a sentence of data. So I'm just going to skip this because I want to get to finish it in a reasonable time. Okay. So what is the, so we tried two techniques here. The first technique is the following. We basically take data, go through a GMM classifier, okay? So imagine this is the speaker ID problem, and the GMM gets the top end speakers. It gives you the top end speakers. For each of the speakers in this n-best list, it has its own Fisher feature space. I compute all those feature spaces here, okay? Give it to this set of all SVMs that I've trained up, right? For every pair of training speakers, there is an SVM pretty much. And it's asymmetric because if speaker I is the positive class and J is the negative class, I have one SVM built out of the Fisher feature corresponding to I. And when J is the positive and I is the negative, I have another Fisher feature corresponding to J. So that's where the asymmetry. So there are two classifiers per pair here. That's why it's C into C minus 1 classifiers. Anyway, so these features are fed into the SVM. You do the sigmoid like I described earlier. And this gives you the posterior scores on whether a certain speaker is positive or negative, in this setting. And you just add all the posterior scores when the speaker competes with all the other speakers, and that gives you a total score. Each speaker, you do the same thing, and then you pick the best. And that's exactly what this thing does. Is it clear? Okay, it's a fairly simple technique. So one minor point I want to mention at the end is, so it's actually a hybrid system which has a GMM in the front end, but the real decision is based on the SVM itself. True, the SVM is initialized. There are two things where the GMM comes into the picture, the n-best list and the Fisher features. Both require the GMM. Okay. So the test that we did for this was on a Lincoln Lab handset database. We had 52 speakers. It was telephone bandwidth speech. And we had data on 4 different microphones. It's a fairly small database for speaker ID anyway. But nevertheless, that's the context in which we did these experiments. The training data is basically 2 utterances from each of the speakers about 30 seconds long. The test data basically is 10 sentences from each speaker, each about 10 seconds long. And you have, so you have a total of 52 speakers times 4 microphones times 10 is about 2,000 odd tests. Okay? So the total number of tests is 2,000. So when I say error rate, it's with respect to this number. Okay, the training. So for each training speaker, we trained 51 binary classifiers which with respect to all the remaining speakers in the Fisher speech corresponding to that particular speaker. So you have a total of this many SVMs that were trained. Testing, you output the best scoring speaker, where each speaker score is the average of the sigmoidal outputs from that speaker's 51 SVMs. Okay? And when you use n-best list, it basically is a smaller size, so you don't take all of them. So this is just for computational reasons. We just reduce it, and so this shows sort of the performance. Okay, so there were 2 systems, since there were 4 microphones, we decided to see how the mismatch scenario performance is. So on the one hand, the baseline is trained with carbon button 1, CB1, another one is CB2, 3, excuse me. And so this shows the match performance of the baseline GMM system. This was on a Kepstrel features, okay, not MLLT or any of this. I'll come to that in a second. So based on a Kepstrel feature system, this is sort of the performance speaker ID error rate. And the hybrid method I just described basically gives you a fairly good relative improvement in performance. In the mismatch scenarios also, the performance improvement is there. Sometimes it's there, sometimes it's very small or not existent. So because of that sort of difference, we tried it on CB3. Again, you find that match condition is a big improvement. Mismatch is less obvious if there's a gain. Okay. And the next thing we did was we said, okay, why are we using a baseline GMM system with capsule features? Let's do an MLT baseline. Obviously, MLT baseline is better. The gains on top of it was not as significant as 25%. Okay? So then we wondered, why is that the case? Can we do something better? And that leads to the second part of what we did in this context. So earlier you had a GMM at the front end. You got the SVMs to make these binary decisions. You combined them, and you got a score, and you made a decision. Now the approach is still slightly different. So this part of it is like what we had in the older system, GMM followed by an SVM that gives you scores. The big difference here is the following. You don't pass all the frames to the SVM. Okay, this process, you only pass those frames where you have a confusion, where you think that the GMM is not able to do a good job. So those frames go to the SVM. So SVM sees, let's say, about 60-70% of the data. It makes its decisions. Those decisions, the scores are not directly added to the GMM. Previously, we just worked on this score alone. Now we are going to work primarily on this score, and we're going to perturb those scores by the scores from the SVM. I'll explain in the next couple of hours what exactly we do. And sort of we combine, get the sort of a hybrids or enhanced score is what I like to call it. And yeah, any question?
How do you define the confusion based on the likelihood scores that are close together, or do you have some development sets and you measure where?
I'll tell you precisely what we do. It's not based on development set. It's based on the test sentence, actually. I'll just mention it in a second. Okay. So it's basically the same database. Training is the same as before. Testing, that's the part you wanted to know. So what we do is, remember in the GMM, for every speaker, for every frame, you have a score. So this is like 1,000 frames. Plop, 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 you have in a speaker 1 scores for the entire set, and speaker 2 have a score, and so on. Think of them as separate rows, okay? Let's look at speaker 1. Here's a bunch of scores. We can find its mean and its variance, right? Now, if the scores are high, it means probably it's that speaker. Low, it means it's not that speaker, it's somebody else. So what we do is we take the mean of the score, which usually is like a nice Gaussian distribution, and take 1 sigma around it. All the frames that fall in that patch are given to the SVM. So it's an adaptive scheme. It really, so you don't have hello data. It's just done adaptively. And I think that's one of the, there are lots of tiny ingredients which all kind of play together to work well. And this, I believe, is one of them. Okay. So those frames are given to the SVM. And since it's, like I said, a Gaussian with 1 sigma, it's roughly 68%, 70% of the data. Now the SVM, basically, what does it do? It takes these things, it does its scoring mechanism through this, does the binary classification, does the sigmoid, does the addition with error control output coding, and gets a score for each speaker. Now that score, okay, in any case, that score is some sort of a posterior, okay? You get a posterior, and let's say that posterior is gamma. Okay, you nudge the GMM score by plus minus gamma times sigma. Sigma is obtained from the GMM, gamma comes from the SVM, plus or minus sign comes from the SVM decision. Is it one side or the other? Okay, so you're adding something to the GMM score which is based on its own dynamic range for that speaker. And you do that for every speaker. So each speaker has a bunch of perturbed scores. You add them all up, that's the total GMM score which is perturbed for that speaker. Do that for every speaker, take the best, and that's your output. Is that clear? Yeah.
Is the SVM trained on all the data or just on ambiguous data in the training set?
It's trained on all the data, basically, in this setup. And the next experiment I talk about, we did it that way, and we did that first, and then we went to this and we did the same thing. So in that case, there was a data sparsity. Here, there is no data sparsity. Okay, good question. So probably if you train on the places where you make errors, you probably could do better, and that's my guess, but I don't know. You are probably guessing the same thing, right? Okay, so speaker identification results. This time, basically, the baseline was an MLLT baseline. Okay, I didn't write MLT here, but it's an MLT-based baseline. So the numbers, if you compare to the earlier case, these 5.4 is a better number. But on top of that, we get a significant gain again, so we brought it on to 3.8, which as far as I know, is probably the best number on this database that I've seen. But it's a small database, but so you get gains of the sort. So somehow, based on my understanding of it so far, the second technique seems to be better. It's actually able to go much better than the first technique, which is kind of telling us a simple story, which is that GMM do pretty well on these tasks if you train them properly. And so there are very few places where you make sort of errors with GMMs because you don't see data for a certain region of the acoustic space or whatever, or you don't model the decision bound in certain regions. Only in those cases you want to bother with these things because SVMs are typically more expensive, and they seem to combine together nicely. The next thing we tried this on was a speaker verification task. There the scenario is simple, right? It is a binary classification task. So verification, basically somebody says, I'm Bill Clinton, and then you have to say whether it's Bill Clinton or not, right? It's not a speaker ID where you have a bunch of speakers and you know who it is. So the training data basically for this, and this, all these are reported, the training and test data is essentially what was used in the NIST evaluation for speaker verification that happened recently. So the training data is a subset of the 1996 and 99 switchboard evaluation. So you need to have a background model, sort of Clinton versus background. So the background is basically all speakers, you pull them together and get some model, called the universal background model in that community at least. Okay, that's built on 4.5 hours of data. As far as each speaker, there are 539 target speakers, and you have a minute of data from each of the speakers. And the way in which you build the model is something like this. You first train a 1024 component Gaussian mixture for the background model. And for each of the 539 speakers, you do map adaptation of just the means to get the speaker's model. Okay? So that's the setup of the training speakers. Then what we did here in the how we incorporate SVMs here is slightly different, which is what we do is for every target speaker, we want to know whether it's the target speaker or the background. I have 1024 Gaussians. Let's use each one of them as a separate binary classifier. Okay? So we had at most 1024 classifiers, but you usually don't have 1024 classifiers simply because the 1 minute of data will hit probably only over 200 or 300 Gaussians on the speaker. Most of the other Gaussians will be starved of data from that speaker, and therefore you only use those corresponding UBM models. Okay? And this is another reason why we have fragmented the data as far as the SVM is concerned, and so we couldn't. Right, so this is the data sparsity I was talking about with the SVMs. Okay. Right. And as for testing, there were 36,620 sort of verification trials. Each one would be a sentence and a hypothesis and a hypothetical speaker, excuse me. Okay. And how do what is the cost function? The cost function is some weird cost. I've never understood this, but anyway, this is what it is. This is some standard cost function. It's just basically a linear combination of the two errors you can make in verification. Either you miss a speaker or you say it's the speaker when it's not. And the weighted combination adds, it's 0.99 and a 0.1. So it adds up to 1.09. This is also a magic I don't understand. But in any case, that number, based on the three systems we have, this is the plain GMM system, no MLLT. Here is a number that shows you how the MLLT usually helps in this context. So it's not just speaker ID, speech record. MLLT generally is a good idea always. You just want to use a diagonalizing transformation because there's no point in using a model that's not invariant to linear transformation of data because it's cheap and free. The enhanced system, this is the one that I just described, has this cost function, DCF, decision cost function, or something called 47. Yeah.
I have a stupid question.
Yeah.
By DCF times 10 to the minus 3, you don't mean that you took DCF divided by 1,000?
Actually, DCF in 10 to the minus 3 units. I mean, that'd be bad news if the error rate is so high.
So it's basically times 1,000.
Yeah, it's 52.2 times 10 to the minus 3. Right. In some scale, relative performance is the same. So, that's the story there. Okay, so anyway, so why does this sort of hybrid technique work? So what I've shown here is the following. You take the GMM scores for a speaker. It's either the speaker or the background. So and you look at the likelihood ratio, the speaker to the background. So you take that ratio and plot it. The likelihood ratio will tend to roughly around 0. So this is the likelihood ratio. This is how you're going to open a window in the middle, 1 sigma, okay, and pass it to the SVM. And it perturbs the score, and this is the distribution after the perturbation. What you see is roughly that it's kind of pushing things out. That you should expect, obviously, because you're doing it. But it's doing it, and it's also improving performance, so it's showing that it's doing the right thing. Somehow the SVM errors and the GMM errors in the middle are very uncorrelated. And therefore, doing this thing by using these two independent decisions, you get a distribution like this with better performance. Okay. So the summary of the second part of the talk is basically that GMM and SVM classifiers seem to produce uncorrelated errors, at least in the speaker ID and verification examples I'm familiar with, and the things we have worked on. Now, SVM can be used for multi-class problems using ECO. See, we just used it. And it's not clear to me that's the best way to combine. There could be better ways. Fisher kernel is one way to get into a high-dimensional feature space where things are probably more separable than the original feature space. But that doesn't also have to be the case. We just chose it. Okay? So both of them, I think, we've just started looking at two techniques, just randomly picked. Hybrid techniques like the two of them that I described today, the hybrid and the enhanced schemes, they seem to work quite well. And so I'm quite excited, especially by the enhanced technique, because it has other advantages. It opens possibilities of using variable frame rate processing. In fact, in the past 4 years, I've always wondered, how do you, when you get a plosive or something, increase the frame rate and get a better model and combine it nicely? And this gives you one way. In retrospect, it's so simple, we should have thought of it 5 years ago. But then, I always thought variable frame rate processing is hard for some reason or the other. But anyway, so this can potentially be done. Audio visual, same thing. One is at 30 frames, the other is at a different rate. You can actually hopefully combine them if you combine them in this fashion. So you have some sort of a baseline system that operates in a certain fashion, and then you perturb its scores based on information from some other system that has completely different features, looks at completely different things, but just gives you the right hint, and you nudge in the right direction. It's a little like it's a little hack, because you're just nudging things, but then I think it's not a bad idea. It seems to give good performance. That's basically it, yeah. Questions?
Any other questions for Ramesh? Thank you. Ramesh, what's your email in case anyone wants to get like a copy of those newspapers or something?
Email. On the web page where you have the abstract, can you just add my email address or something?
Okay.
That's easier, right?
Sure.
Then,
Also, you have a URL, and the URL gives you.
oh yeah, yeah.
The web page already has your URL.
Oh yeah, so yeah.
It's,
Combining those.
Right.
Do you have a feel how much the performance improvement comes from the SVM performance and how much does come from the classifier combination?
Yeah. Honestly, I don't have a clear answer, but if I were to guess, I would probably, based on whatever numbers we have seen so far and how we have got to this point, I would guess the error correction mechanism is probably a little more useful than finding the decision boundary with the SVM directly. So in other words, I would say the combination does play a big role, because the reason why we had to go to this flat sigmoidal scheme for combination was because the first scheme we tried was just take the scores and combine them, and it didn't work quite well. Nowhere close to 20% relative gains. So we had to fix the combination in the right fashion to make it work. So based on that, I would guess combination is probably more critical, but I'm not giving a logically correct answer showing that that's the right thing. So that's just a guess.
Okay.
Yeah.
Thanks again, Ramesh.
Yeah.
Lunch in department 117.